Here is an example of multiple population proportions hypothesis testing. We're going to test whether the population proportions are all the same or at least one is different. In this example, we are looking at a consulting company that is doing an analysis of customer loyalty for brands. So we are looking at three different automobile owners, Chevrolet Impala, Ford Fusion, and Honda Accord. So population of Chevrolet Impala owners, population of Ford Fusion owners, population of Honda Accord owners. And from each population, we take a sample and ask them whether they will repurchase. If when they are ready to purchase another vehicle, will they purchase the same vehicle as what they own right now? Okay. And then P sub 1, P sub 2, P sub 3 are proportion of owners who are likely to be loyal to their brand. P sub 1, P sub 2, and P sub 3, and we want to test whether they are all the same. So is brand loyalty the same for these three different brands? So we take samples and the sample information is given here. Okay. So Impala, Fusion, and Accord owners, we take 125 Impala owners, 200 Ford Fusion owners, 175 Honda Accord owners, and each sample we record how many showed loyalty, meaning that they said, okay, they will purchase the same vehicle as they own right now. So with this, we want to test this hypothesis. So let's look at the Excel file now. Okay. So first we need to define the population and the three population proportions, and we also will look at the hypothesis, null, and the alternative. Okay. Population is automobile owners of these three different brands. There are three populations actually, and we have P sub 1, P sub 2, P sub 3 defined as being loyal to that particular brand that they currently own. The null and the alternative hypothesis, we've already seen that, so let's set that up now. Okay. All three population proportions are the same. Not all of them are the same. So now here is the data that is given in the text. So now what we need to do is to apply the formula for expected frequency. You have to find the sum for each row. Okay. Let's copy that down, and when we copy, that border line will go away, so we need to put that back. Now we sum the column and copy that. Okay, and then we copy one more time, so that would be our grand total, the total sample size. Okay. So now we have to set up the expected frequency, and now we have to be real careful here. If we set it up with proper absolute references, then all we need to do is to set the formula up once, and then we will be able to copy everywhere. So when we are copying, some of these cells, column should change, but the row should not change. Like for example, the row total must always come from this row. Okay, it should not change rows, but the columns must change. The column total should always come from this column, but the rows must change. But the denominator, the total sample size, must always come from this particular cell F17. So here we start with the row total. For this cell, this is the first row, so we take the row total for the first row. And remember, that should always come from column F. So the dollar sign, you have pressed F4 a few times, the dollar sign should come for F and not for 15. So when you copy it down, F15 will change to F16. But when you copy across to the columns, it'll always be F. Okay, it won't change to G15 and H15. So times, and here this is C17. This time the dollar sign should go to 17. So when you copy across to D and E, it will change to D17 and E17. But when you copy it down to this cell, it will remain at C17 divided by the grand sample size, and that should be $F $17. So if you set it up in this fashion, then you don't have to redo the formula every time for each of those cells. And this is important, and I will be grading on this basis. Okay. Now you copy that way and copy down. Okay. These expected frequencies can be non-integer. So now put the border back. Now if you sum, so we can copy the sum formula from here. It should be exactly same as the observed frequencies. You can copy the column sums from there like that, and you see that they are exactly same. If they are not exactly same, then there is some mistake somewhere. So now we are done with the expected frequencies. So the next step is to compute the chi-squared values. Chi-squared values, we already saw the formula, so that is the observed frequency minus expected frequency. So here, start with a parenthesis, observed frequency minus the expected frequency, and we have to square that difference divided by the expected frequency. Okay. Now let's, we don't need, okay. Now copy that across for the other two columns in the first row and down, and of course the border needs to be put back. Okay, these are the individual chi-squared values, and when you sum all of these different chi-squareds, then we get the calculated value for chi-squared. Now we want to test for an alpha of 5%, I think. 5%. K minus 1 is the degrees of freedom. You use count A. Okay, and there are three populations, so count A minus 1. So that gives you degrees of freedom of 2. Now we can test using the chi-squared table value. Chi-squared table value is chi-sq.inv.rt, the right side. Okay, alpha, comma, degrees of freedom. So that gives you the chi-squared table value, and if chi-squared calculated value is greater than table value, then we reject the null hypothesis. Not all the brand loyalties are equal, and in this case we do reject the null hypothesis. So the conclusion is reject null hypothesis. Okay. Now we can use the p-value approach. The p-value is given by chi-sq.dist.rt. So now we use the chi-squared calculated value and the degrees of freedom. So that will give us the p-value. Make that into a percentage, and if the p-value is less than or equal to the alpha value, then we reject the null hypothesis, which is the case now. So we do reject it, like in this case. Now obviously both conclusions must be the same, except that we say it differently. Okay, now we need to interpret. So we have sufficient sample evidence to conclude the brand loyalties are not all the same for the three different brands, and the probability that this conclusion is wrong is 1.9%. Okay. Now that we've rejected the null hypothesis, we will do a multiple comparison procedure in the next video.